Okay. So today we are going to talk about shifted geometric sequences. So this is 1.3 shifted geometric sequences.
What happened to the bottom?
We can get that done. Yes, at this point, I'm not really telling you which pages to write down in your portfolio sheet. I'm just assuming that you're doing it and writing the page numbers and that the things that you say are there are where they're supposed to be. Okay? Make sure you do have 2 colors at least. I prefer 3. You want my markers? They're over there.
So will we never get to the outlines? Or we thought we'll get to the
You have the paper in there, but you can take it out if you'd like to.
So what happened with ball downs?
We didn't have time. We had too many things going on in class.
Okay,
Didn't get time to do it.
so instead of that, it would be this, right?
Yep. You can just leave it in there if you want to. If it's easier, just leave it alone. It's already in. So, shifted geometric sequences. Everybody's got their writing utensils? At least 2 pretty colors. Alright, first let's review. Let's talk about arithmetic sequences. Arithmetic sequences are linear relationships. They look like a line. When they are graphed, they create a line. Like this. Over here. And with lines go on forever, positive and negative. Yes? They go forever in the negative direction and forever in the positive direction. You keep on going. You can go as long as you want to. Geometric sequences do not go on forever. Geometric sequences are always approaching 0. They approach 0. They do go on forever, but they don't hit all the values.
Oh,
They never will get negative.
Yeah.
Arithmetic sequences can be negative. It's not that they can't be negative, it's that they will always approach 0. Like their values will be getting smaller and smaller and smaller. They can still be positive and negative values of n. They can be on either side of this. But they are getting closer. They're always getting smaller or getting larger, headed to 0. Okay? You can't always see it, but in the graph is where it matters. In the graph, if you look, you can tell this is approaching 0. If you were to continue it out, it is getting closer and closer to the 0 line, to the axis.
But it will never cross the...
It will never cross. It will just get infinitely close to 0. Alright? It's getting smaller and smaller going that direction. But this is a growth. So often, the only part of this graph you see is the part that's going up. It's important to realize that behind that, it is still going closer and closer to 0. And decays are a little easier to see because they're usually written like this. And they continue, they get closer and closer and closer to 0. Okay? Yes?
But how can you have negative days? Like if
Negative.
like if the part that goes down to 0, the first graph, it can be
Usually you
negative.
can't because logically you know that things can't be negative. Some things just can't be.
Mm-hmm.
This isn't talking about that. This is saying in the graph sense.
Oh.
If you're looking at the graph, arithmetic sequences are lines Geometric sequences are approaching 0.
Okay.
Okay? And that brings me to the next point. Thank you, Ivy. Common sense matters. Some things can't be negative. You can't have a negative number of people. You can't have half a person. Some common sense matters. You have to think about what your numbers are talking about. Negative numbers don't make sense in some situations. Getting infinitely close to 0 but never hitting it doesn't make sense in some situations. Like a ball doesn't bounce forever. We don't keep things in our bloodstream forever. Common sense matters. Okay? Remember that these are just models. They're not real life. Let's talk about shifted geometric sequences. These are geometric sequences. Geometric sequences that approach values other than 0. So, not 0. The most important thing about shifted geometric is to realize that their graph, they are not approaching 0. In the long run, a geometric sequence will even out to 0. A shifted geometric sequence will not. It will even out, but to a different value. Okay? A value that's not 0. Just like with the medicine, it does level out, but it's leveling out at a different value. It's not going to 0. That one was going to 300.
And that is what?
That is where they are headed. Well, just a second. We'll talk about it. We call it the long... Dang it. Misspelled. Fix misspelling. The long run value. In the long run, eventually, the value it will reach. We call it the long run value. The value it is approaching...
Other than 0, not 0?
Not 0.
Then why does it say 0?
What?
There were like geometric sequences that approach value other than 0, not 0.
Yep. So you're approaching something that's not 0.
Oh.
Anything that's not 0.
Okay.
The value it is approaching is called the long run value. We have some other names for it. It's referred to as a lot of different things, but long run value, sometimes it's called the limit. Sometimes it's called the break or the stabilizing point. The part where it starts to even out. And on a graph, it looks like this. It would be the point that your graph is going towards. So your long run value is right here. Okay, it's the spot where it's starting to even out.
Oh, but it doesn't touch.
It doesn't touch it. It never reaches it. It gets infinitely close to it, just like geometric sequences get infinitely close to 0. So geometric sequences are just, or shifted geometric sequences are just geometric sequences, but they have something a little extra. Okay?
Why is
Yes.
there like a big gap between limit and stabilizing point?
Because of my handwriting.
Oh, that's sorry. I thought
I
it was
just
like
jumped.
a reason.
I didn't have a reason.
How'd you do that?
I grabbed it and moved it. Magic. So, geometric sequences look like what? What's the general form of a geometric sequence? We're talking the u sub n, the rule. What does the rule look like? U sub n equals what?
U sub n minus 1
U sub n minus 1.
times 1 plus n.
Remember, the ratio.
Or-
But yes, 1 plus something or 1 minus something. That's what the ratio is. But it's just times the ratio. Okay? So, shifted geometric sequences, which I'm going to shorten to SGC, no, dang it, SGS, shifted geometric sequences, look exactly the same. U sub n minus 1 times r. Oops. But they have a little something extra. They have both a ratio and a difference. Does that make sense?
No.
What does it say next to geometric sequence?
SGS, shifted geometric sequence. I just didn't really bring it out. A shifted geometric sequence is a geometric sequence with something else added. We just did one. We did the medicine. It was multiplied by 0.75, right? We took 20, she lost 25% every time. But then she added 16 milliliters also. So her body filtered out 25% for the ratio. The ratio was 0.75. But then she added 16 milliliters every day. Does that make sense? We following? Good. We continue talking? Let's look at an example. Maybe that'll help.
Wait,
Yes.
are you gonna take it off?
What?
You're gonna leave it, right?
I'm just scrolling.
Oh.
So, Hannah and Harvard are working at the pool for the summer, and they need to provide a shock treatment of 450 grams of dry chlorine to the pool to prevent algae growth. So it's just like they're throwing a whole bunch of chlorine in there to kill all the algae. And then they're going to add 45 grams each day after that initial treatment. Okay? The sun's going to burn off 15% of the chlorine. It's going to make it evaporate each day. And we're going to look at the different amounts as the sun burns away some and they keep adding. And see how it turns out. So, first of all, what's my starting value? What is it, Julius?
450 grams.
So U sub 0, 450 grams.
Yeah.
Okay.
And
So now I need my rule. Remember, I've got my generic form up here.
yeah.
U sub n
450.
equals U sub n minus 1. What's my ratio? How much?
10%.
How much is being burned off each day?
15%.
15%. So how do I write decaying 15% as a ratio?
Point eight.
It's no, it's in one times.
Point eight one.
1 minus 0.15. It's just a decay. And at this point, we're just geometric. This is just a geometric sequence like all the other geometric sequences. Yes.
Why do you put 1 minus?
You don't? You could write 0.85. I'm just clarifying what I'm doing. If I just wrote 0.85, they'd be like, where'd you get that? Where'd you get that? So, it's 0.85. It's just saying the whole minus 15%, which is what we did when you were peeing. We took 25% of how much was in your blood and we subtracted it.
So we could also write times 0.85.
Yes. And then this has got one more piece. What else is happening each day?
In that, they add 45 grams.
Keep adding 10%.
They're not adding 10%. How much are they?
45
Well, it is
grams.
10%, but yes. Yeah, 10% of their initial. So they're adding 45 every day. Okay? So this is multiplied by a ratio, but it's also adding a common difference every day. Both those things are happening. So let's look at what that's going to do in the long run. 'Cause remember, we said that this is going to it's going to keep growing. Or this one, actually, in this case, it's going to decay. But it's not going to go to zero. It's going to level out at a certain point. That's why they're adding 45 grams every day, because they want a specific amount of chlorine to always be in the pool. So, to figure out what that's going to be, there's two different ways to do it. There are two ways to find the long run value. Use blue. Two ways to find the long run value. One way is just by looking at the graph. If you start graphing it and you take it out far enough, it'll be getting so close to a point that it will be like within a couple decimals of itself. It's not really changing, and you can figure out what it is. In this case, if you look, you see they took it way out to 30. It's leveling out right here. What do you think that value is?
300.
Looks like 300. So with the graph, if you graph it and you take it out far enough, you can tell that it is starting to level out following this system at 300 grams. They will always have 300 grams in their pool if they keep adding 45 every day. You can also tell with algebra. If you're looking at this and you're saying, I want to know when is this going to be the same? When is one term and the term before it going to be basically the same term? So that from one step to the next, it's hardly changing. Well, I'm going to replace u sub n and u sub n minus 1 with the same variable. Because I'm saying, when will these two things be the same? So let's make them fictionally the same. I'll show you. So instead of u sub n, we're gonna write, I'm just gonna use c. Instead of u sub n minus 1, I'm also gonna use c. I'm gonna say times 0.85 plus 45. Okay?
C is what?
I just chose one. You could have used anything. I'm just making these two things, one term and the term before it. I'm saying in this sequence, when does it happen that these two things are the same?
Oh.
So I'm replacing them with the same variable.
So
So between,
you could also say A.
you could say whatever you wanted, as long as they're the same. I'm just trying to make them the same. So,
wouldn't it be c minus 1?
no, because I'm trying to say, at some point in this list, like if I have a list that goes like 1, 2, 3, if it was getting closer and closer and closer to the same value as it went on, like this, if it's like, let me take a 1.9, 1.999, 1.999999. I'm saying at what point is this one 2 and the next one's also 2? When are they the same number? And yes, like we know that's not actually going to happen, but theoretically, when would it happen? We can figure that out with algebra. So instead of writing u sub n and u sub n minus 1, I'm just going to put variables. Okay? So now I have c equals 0.85 c. I'm just rearranging c times 0.85. I'm going to write it 0.85 times c plus 45. You know how to solve that?
Yeah.
What's our
30.
first step?
You got 3 corner?
We need to get something all on the same side.
Oh,
Let's
c.
need to move c to the same side.
Yeah.
Minus. Hold on, let me walk through it. People's refreshing. This is the first time we've done this in a while. Minus 0.85c minus 0.85c from both sides gives me, on this side, these cancel out. I just have 45. On this side, what is 1c minus 0.85c?
15c.
0.15c.
0.15.
Can we do the last?
Can we back up a step?
Yeah.
So, we had 0.85c plus 45. I subtracted 0.85c from both sides. Okay?
What are the minus -0.85.
That's just that's what I'm doing. I'm moving things to the other side of the equation to try and
Oh,
balance.
okay. I see.
This is solving for x.
I got it.
Oh yeah.
And
So I'm
This thing
subtracting the
is-
0.85c from both sides.
But there are only one.
Two?
I'm just writing it from both sides. So I'm subtracting it from the right side, and I'm subtracting it from the left side. Because what you do to
Where is
one
it on the
side,
left side?
it's not. But what you do to one side, you have to do to the other
Yeah.
as solving, right? So what I do to this side of the equation, I have to do to this side of the equation for them to stay equal. So because I want to get rid of this from here, I have to subtract it from this side and subtract it from this side.
But then, Miss Davy,
But C is 450. No.
C is not, we don't know yet. That's what we're trying to
we
solve
have
for.
1.15 of a C.
Yep.
Like it's a fraction of a C.
Okay.
So, 0.85c minus 0.85c, guys. These cancel out. This is 1c. 1 minus 0.85 is 0.15. So now we're at 0.15c equals 45. How do we get c by itself?
You have to
You have
multiply
to
multiply point.
Not multiply.
divide
by
45 from both sides.
Nope, you want to get c alone.
Divide 0.15.
Divided
both
by
sides.
0.5.
Get 0.15 out of there. So we divide by 0.15, leaving us with c is equal to what?
300. 300.
The 3.
No. You have to no. Oh, I get it. It's
Yeah, 300.
Then that's what we found in the graph. It's the same thing. There's two ways to do this.
No.
It is not always
That's
easy.
Not, that's not hard.
It is not always easy to look at the graph. Sometimes you're given the graph and it's easy to be like, this is where it's leveling out. Do it right here. That's my long run value. Sometimes you'll be like, nope, I don't want to spend hours making this graph. So instead, you can use the algebra method to find the long run value.
and test we will be able to use a graphing calculator.
Oh yeah. I'm going to be passing graphing calculators out to the tables eventually. I'm waiting for containers to sit on the tables. They're not
Okay.
here yet. Yes, ma'am.
So then, like, the actual formula would be like C equals C times R plus D.
Yes.
So the answer is 300 grams.
Yes.
Okay, great.
That's the value of chlorine that will be in their pool eventually, if they keep following this system.
300 grams.
Mm-hmm. So let's summarize. Important things. Remember, these are the important things I need you to know. If you remember nothing else about what I said today, you need to remember that geometric sequences approach what?
0.
Approach 0. And shifted geometric sequences approach what?
A value other than 0.
Something that's not 0. Shifted. Geometric. Approach. Not 0. Something that isn't 0. Could be 20, could be 100, could be 3,000. Something not 0. The only other thing you need to remember is that you can find the long run value algebraically or graphically. So, finding the long run. Graphically or algebraically. And what makes a shifted geometric sequence special? What does it have?
It has a ratio and a difference.
It has an added value and it has a ratio.
And
So
Oh.
shifted have ratios and they have an R and a D. Okay? They have a ratio and a difference. There's something being multiplied, there's
Right.
something being added.
Graph 1. Graph 1.
For which part?
Long run value and then.
It just says long run value graphically or
Should they
algebraically.
have R and D?
You could find it graphically or algebraically. Your homework is sitting up where it usually is. It's gray. Homework is a gray sheet today. Here you go, Ivy.
Can they get me one?
Yes.
Well, my cousin is like, okay. He's like, no, no, you can.
Yeah.